Welcome to Mythosium, the place where the deepest ideas in science are transformed into clear, intuitive explanations. Today we're exploring a concept that sounds simple at first, but quickly becomes one of the most mind-bending ideas in modern physics: the notion that empty space is not empty. From childhood onward, most people imagine space as a vast void, a clean, silent backdrop containing stars, planets, and galaxies. Even the space between the atoms in your body feels like a kind of nothingness, a calm vacancy in which matter resides. But the closer scientists look, the more this picture dissolves. The emptiness inside atoms is not a dead vacuum, and the vacuum between particles is not a flat, passive nothing. Instead, what we call empty space is a churning ocean of invisible activity, an arena where energy fluctuates, fields ripple, and the fundamental ingredients of matter flicker into and out of existence at unimaginable speeds. Today we'll explore why this happens, why space cannot be empty, how this phenomenon shapes matter itself, and why our existence depends on it. To appreciate this fully, let's start with a familiar idea: the atom. An atom consists of a dense nucleus surrounded by a cloud of electrons. If the atom were scaled up to the size of your arm span, the nucleus would be smaller than a single human hair placed at the center of your chest, and the electrons would be whizzing around near your fingertips. The space between them, the overwhelming majority of the atom's volume, appears to be empty. And because all matter is composed of atoms, everything around us seems to be constructed mostly from nothing. But even this nothing is deceiving. Zoom in far beyond the electron cloud into the nucleus, and you find protons and neutrons. Zoom inside the proton, and you find quarks and gluons. But if we zoom past the quarks themselves, past the level of particles we're familiar with, we encounter something stranger than any simple void, a roiling, fluctuating quantum field that never rests. The modern understanding of nature comes from quantum field theory, which states that every particle, quark, electron, photon, gluon, is actually a tiny vibration in an underlying field. These fields extend throughout all of space. They are not in space. They are space. Even when no particles are present, the fields remain, and they cannot lie perfectly still. The laws of quantum mechanics require them to fluctuate. These fluctuations are not errors or noise. They are fundamental. The closer physicists examine these fields, the more structure appears. The quark and gluon fields in particular produce some of the most dramatic behavior. In the vacuum, they fluctuate so violently and so rapidly that sophisticated supercomputer simulations are required just to glimpse their behavior. These simulations reveal patterns of rising and falling energy density, bright spots where the field is briefly intense, surrounded by shifting lower energy regions. If we could observe this at real speed, it would play out in intervals so short that 1,000,000 billion frames would pass every second, and yet the region being simulated is incredibly small, a space just large enough for two protons to fit side by side. But in the simulation, no protons are present. This is the vacuum on its own, pure empty space. And even here, every point flickers with activity. This picture of the vacuum contradicts everyday intuition. We expect that removing all matter, all radiation, all particles, and all fields should yield a perfectly silent zero. But the vacuum state of quantum fields is not an absence of energy. It is the lowest energy configuration allowed by the laws of physics. And this lowest energy state still contains fluctuations, because a perfectly motionless field is forbidden. To eliminate all fluctuations, to create a truly empty vacuum, would require adding energy, not removing it. And even if such a pure vacuum were created, it would be unstable. The slightest disturbance would cause it to collapse back into a fluctuating state. Counterintuitive as it sounds, nothing is not the natural condition of space. Something is. This idea can be related to more familiar systems. Consider a magnet. At room temperature, the magnetic field exists because atomic spins align with one another. To remove the magnetism, you must heat the material until those spins become so disordered that the alignment vanishes. Removing the field requires inputting energy. Similarly, clearing away the fluctuations of the quantum vacuum would require adding enough energy to push the system into an unnatural empty state, one that would instantly fall apart. The fluctuations in the vacuum play a critical role in shaping the behavior of particles. Inside a proton, for example, the presence of quantum fluctuations influences where quarks prefer to exist. They tend to gather on top of localized regions of high gluon field density, an effect uncovered by studying the structure of protons in detail. These localized regions, brief ephemeral lumps of energy, appear and vanish rapidly. A quark inside the proton seems to hop from one such lump to another, riding the ever-changing landscape of the field. One way to imagine this is to picture a hiker crossing a stream. The water churns unpredictably, and occasionally a stone appears above the surface. By stepping quickly from one stone to the next, the hiker moves forward without falling into the water. In a similar sense, quarks step through the vacuum by jumping between fleeting regions of enhanced field density. This hopping behavior is not just a metaphor. It is part of what determines the proton's mass, structure, and stability. Even though quarks themselves are incredibly light, the dynamic dance of quarks and gluons interacting with the vacuum creates the majority of the proton's mass. In fact, nearly all the mass of ordinary matter does not come from the mass of the individual particles, but from the energy stored in these quantum fields and their constant fluctuations. The vacuum, in other words, holds up the world. If empty space were truly empty, if no fluctuations existed, the structure of matter would collapse. Quarks cannot behave as they do. Protons and neutrons would not form. Atoms would not cohere. The universe as we know it would be impossible. This insight forces us to confront an astonishing truth. The universe is not built from solid, stable, indivisible particles sitting in empty space. It is built from fields, all of which are constantly vibrating, interacting, and influencing one another. Matter is simply what happens when certain field configurations become stable enough to persist. Space is the stage on which this occurs. But the stage is alive, restless, and full of structure. The vacuum is both the simplest and most mysterious object in all of physics. Its fluctuations give rise to forces, allow particles to interact, contribute to the mass of matter, and shape the behavior of the universe at every scale. And yet, despite all of this, the vacuum remains invisible. Its activity happens at scales too small and timescales too fast for ordinary perception. Modern physics is still working to fully understand the vacuum. Its energy content may hold clues about the expansion of the universe. Its structure may be tied to the origin of mass. Its fluctuations may play a role in quantum entanglement, phase transitions, and the nature of time itself. What we call empty space is not the calm, quiet backdrop we once imagined. It is an ocean of energy, a dynamic fabric woven from fluctuating fields. Matter rides on top of it. Forces arise within it, and existence depends on it. Here at Mythosium, we explore ideas like these not just because they redefine our understanding of reality, but because they show how the universe is far stranger, more dynamic, and more interconnected than everyday experience suggests. If you enjoy discovering the hidden structure of nature, from the deepest quantum fields to the largest cosmic patterns, make sure to subscribe. There are countless mysteries still waiting beneath the surface of what we call nothing. Thank you for watching, and stay curious.